Okay, so I'll discuss my name is Milan Mandic, and I was a team that was working on the line of sight control, the inner loop control as well acquisition. So this part is on the line of sight control feedback results. There are a lot of people who contributed, but in the interest of time, let's just get going. So in for the line of sight control, first I would like to introduce the what we actually wanted to achieve. The main objective was there are a couple of different objectives, but one of the main ones was to basically bring the down to less than 1 microfarad on the traffic axis. So the main source of our pointing errors, the disturbances, coming from two sources. One is the ACS, which is typically a very low frequency around the bandwidth of the ACS. And the other one is from the jitter generated by the reaction wheels. And so the reaction wheels, the source from the reaction wheels is due to the static and dynamic imbalances. It's basically very dependent on the frequency at which the reaction will spin. And so we've noticed through a lot of modeling that the main disturbances are appearing around the fundamental at the fundamental frequency. And so, as you can imagine, if you spin those wheels really fast, you're going to get a very large, potentially large disturbances at a very high frequencies, and those would be very hard to control. And so, what we've done actually in a collaboration with the ACS team at Goddard was to limit the reaction wheel speed during the CGI observations, and the agreement is to go up to 5 revolutions per second or 5. That basically gives us the most of the essentially. This meter doesn't work. Not there we go. So you can see that they're basically staying during the observations, which is these longer periods. During those observations, we're trying to keep the reaction speed within approximately within 5 hertz. So because of that, we might be crossing the zero crossings more often than we would like. And so those offload, in order to basically stay within 5 hertz or 5 revolutions per second, the offloads essentially happen. I can't really aim with this, but during these slews and rolls. So during the slews, when we're going from one star to another, we basically offload the reaction wheel so that we can remain inside of that low frequency range. That allows us to actually build a controller that's still, in relatively speaking, it's actually compared to ACS, it's a very high frequency, around 20 hertz. And so in order to actually implement a 20 hertz bandwidth controller, we can't really do that on the applied software. So all of this was actually implemented on the FPGA. We also have, that's the line of sight loop, which also is sitting on top of, and actually, I'll get to that too. And so the idea is that with the 20 hertz bandwidth, we can essentially meet the requirement of bringing the disturbances down to less than 1 milliarc second, based on the requirement that we have 70% of the time. We actually can meet it much higher percentage than that. And in order to actually evaluate how this works, how well we perform, because the reaction was can vary, and you basically get a very different disturbance depending on the reactional speed. So there's a very large combination of reaction. We did the Monte Carlo study and we evaluated it in the simulation. So that's first part of what we needed to do for the line of sight. That's one of the major ones. The other one was also to demonstrate that once we land somewhere on the mask within the 80 milliarc second range, we need to be able to bring the star by lock when we bring the star down to the center of the mask, to the training point. And so all right, so So the main objective of the TVAC testing was to essentially show that we have the rejection capability of our designs, because that was run through the Monte Carlo study. So if we can actually meet the disturbance rejection in the TVAC, we can extrapolate that we actually can also mimic the performance through the Monte Carlo to the design that we have. Because we couldn't do the Monte Carlo for all these various reactions in the TVAC. And so we've actually first demonstrated the functionality of the system through risk reduction testing and FFT testing. And then the TVAC eventually provided us with a clean enough signal that we could actually do some performance analysis. And so both objectives are the capture and the injection capability successful. So this is a brief so this is our block diagram, and very briefly, this is the line of sight control here. We are receiving measurement from the locus estimator, which is also located on the separate FPGA. Being on the FPGA complicates implementation, but also buys us very low delays in the system. So we basically are removing the bottleneck of communication between flight software and the FPGA, and that allowed us to actually reach a much higher bandwidth control. So we're basically living right close to our actuator and directly in flight software. Internal to the FSM, so we actually have nested loops. The outside of the outer loop in the line of sight control, but inside of the FSM, basically on the FSM level, we have the inner loop, which is actually a loop that's basically closed only on the strain gauges. That basically allows us to have a flat response up to very high frequency, about 100. And what also it removes all the hysteresis and creep effects that we might experience with the FSM. And so by getting that flat response with the inner loop, we were able to close the line of sight and demonstrate 20 hertz, close to 20 hertz, not exactly, but about 20 hertz. So quickly, this is just a kind of a PR chart. So we actually ran. This is actual data from the testing. This is what we were looking at while we were testing. So what we did, we actually introduced this disturbance signal that's flight-like, based on the modeling that was done at Goddard. And so we generated the disturbance signal on using the ACS disturbances and the reaction wall disturbances. We had the model for the reaction walls actually capture 73 harmonics, but really what was hurting us the most were the fundamentals, and maybe here and there first or second harmonic, depending if we hit some structural motors, so in the model. But essentially that we generated these disturbances that represented the disturbance signals. And so this is about 10 minutes of the data. And then so this is only in one axis, and then this is the corresponding C3 axis. And then we actually ran the same signal. We closed the loop, and then we ran exactly the same disturbance signal. And we basically shows how we eliminate a large chunk of the disturbance. So this is the movie. This movie was actually done at a separate time. We started with the disturbance, and then during the disturbance, on this disturbance is being played, we close the line of sight loop and we stabilize the image. So on this, you can see that it initially starts with the disturbance. Once we lock the loop, you can see that the image becomes very stable. And so this is actual data from the test. Sample performance, again, I say sample because, depending on where the reaction was, you're going to get different levels. But in this case, we're actually seeing about the other control we were running in this specific case was close to 5 milliarc seconds in one axis and over a little more than 6 milliarc seconds in the C3 when we close the line of sight loop. we were actually can't really aim with this. My pointing with the control, we actually cut it down to much less than milliards second level. Anyways,
We'd rather have you for this.
yeah. Okay, so what was the approach that we took in order to come up with to evaluate the performance? Well, we introduced something called a shorter signal. It's basically a glorified time sweep. It's very helpful because we put the energy exactly at the frequency that we care about, and then you can essentially see the response. You can easily measure the response. So what we've done, we actually ran this is just one of the. This one is just one of the samples in the beginning of the signal. It's a alignment signal, so you can see just doing the alignments. And then this is the signal that's being introduced. The blue one is what is being introduced at the disturbance, and the red one is what comes out as the out. So don't get too tricked that there is a diminished return here at the very end. And actually, just tracking of those signals was not very good. So actually, it's from the jitter mirror not being able to track those high frequency signals, but really the response that we hear about is in that lower frequency range. As we go in the higher frequency, the noise, the signal is not as clean, and so we don't get very good results. But what we do care about is at the lower frequency range to essentially see the rejection capability. And so you can see that with the line of sight loop curve versus the yellow curve when we turn on the loop on, and you can see that in that frequency space from 0 to about 15 hertz, we're getting the response, the attenuation of the disturbances. And that, as you probably know, the bandwidth, we don't get the same type of rejection at every frequency. It actually diminishes as we're getting closer to the bandwidth. And so that's why we wanted to keep the reaction wheels limited to 5 hertz, where we actually have up to 5 hertz, where we have the best chance of doing the most rejection. And so that same plot, the rejection capability, and as you can see that the Z2 and Z3 are actually very close on top of each other, but more importantly, very close to the blue curve, which is what the design. So that basically showed us that we can match the demand time performance, and by extension, we can claim that based on the Mandic power study that we've done, and use the 1 linear cycle cloud. This is just one of this is actual data from the testing where we have the disturbance and in the blue color, and the red color shows the loop, what kind of how all of these modes are basically being attenuated. And we basically evaluated that we have a bandwidth of about 17 hertz. The design was about 18 hertz, and so we are very close. The data is not the most forgiving, but it's about 17 hertz that we're getting. The next one, so in addition to the line of sight rejection capability, we also wanted to demonstrate the capture. And so in the interest of time, I'll just focus on the picture number 3. And I don't know if you guys can see, but the goal here was to actually capture a star 80 milliseconds away, which is our basically our limit of what you wanted to at the end of the range. So these plots actually represent the central point, and I have to thank Clem for generating this capability during the testing. But what 0 point location represents is where the FSM actually currently is, where it starts. And so when we want to close the line of sight loop based on, so the star is actually located 80 milliseconds away, and so we need to find it at that location. And so what we do is we try to We try to lock the line of sight loop. And because the low-FUS is not a linear sensor, so it's linear only in a very limited range. But as it goes further and further away from the training point, the nonlinearities, significant nonlinearities kick in. We don't take a straight path. So if it was a perfectly ideal estimator, we would essentially go directly. We would just go from 0 straight line to 80 milliarc seconds, and we would find the star. We would nail it there. However, because it's not, we take a roundabout way. We actually could even go into the wrong direction until the gradient path, the gradient field, essentially allows us to bring ourselves back to where the star is located. So there is in vast majority of cases, we were actually successful. There were a couple of cases that we actually did not manage to acquire. Those happened when we had a lower EM gain on the camera, so the signal was not as boosted as it could have been. And what I think happens is we end up being somewhere in the local minima, and we get stuck in the local minima, and we don't recover fast enough. And fast enough basically means that the signal that we are measuring of the star being on the mass does not recover inside of these thresholds. And if it doesn't recover after a certain amount of time, we trigger the pole protection monitor. So because there was a delay in when the flux was being recovered, we were very close to, in many cases, we were very nervous. Is it actually going to capture it? Because we might actually trigger the fault protection, then we have to go through the whole process. But so this is one of the key examples of how it works. And again, this is the morphology that everybody recognizes now that we care about. We tested in from multiple locations. Some of these tests actually happened in air tests as well. We've done in different locations with different magnetic stars. We actually covered a large area. There is one contribution. If you noticed on one of the slides, I showed the performance up to 175 hertz from 0 to 175. Well, there was a high frequency disturbance at 180. So so the funny thing about this one is that it only shows up in a Z3 channel, and we did some studies trying to figure out where this additional disturbance is coming from. It's not deal breaker, but it is significant. And so we've discovered that we actually see, if you can see this sharp line increase here, that shows up around 180 hertz. We identified that to be essentially a harmonic. We know those are not going to be in flight, and so we are actually, this is expected during the testing on ground. However, there is around 190 hertz and a smaller component around 210, where we suspect this is some kind of a structural mode that is being excited, whether internal on the instrument or external, the CBS, the source that's generating the disturbances. We're not 100% sure, but we are essentially seeing the around 190 hertz mode also show up at the CBS location. This may not justify the size of it, but the fact that the CBS is actually seeing that mode as well implies that it might be an external source. So we unfortunately didn't have the exact source identified. But even with the even if it is part of the disturbance, internal disturbance, if it's real, we are still very close to about 1 milliarc sec, even with that disturbance. And there are many cases where we actually don't even grade the. So that's the caveat in all of this testing. And the funny thing is, it only shows up in Z3. We have not actually seen this component in Z2. Z3 is, if you will, it's going up and down on the bench versus left and right. And so if I'm So basically, again, summary, it was successful that the disturbance rejection as expected, and we actually demonstrated the range.